Hello everyone, and welcome back to Tech Forward. I'm Jenny, here as always with the man who apparently dreams in silicon these days.
Laughs. That's a new one, Jenny. Maybe a bit close to the mark this week, though. I'm Mark, and my brain is still kind of processing everything from Nvidia's GTC.
I can only imagine. The headlines were flying, big chips, big numbers. It felt like a lot. I definitely need the Mark breakdown. What specifically has your attention?
Okay, so the big data center chips like the B200 were impressive, naturally. But what really snagged my interest, maybe because it feels a bit closer to home, were the new Times desktop systems they announced. The DGX Station and the DGX Spark.
DGX Station. Okay, that rings a bell. Weren't those the, incredibly expensive black boxes you'd see tucked away in AI research labs? The under-the-desk supercomputers?
That's the lineage, exactly. Those were the previous generations. But these new ones are a whole different beast. They're built on the brand new Grace Blackwell architecture, specifically the GB300 Grace Blackwell Ultra chip for the main station. We're talking about putting genuine data center compute power right into a standard office or lab. Think about skipping those cloud queue times for certain tasks.
Hold on, rewind. Data center performance in something that sits near your desk? That sounds powerful, maybe even excessive. What exactly is powering these things? What's under the hood?
Right, let's get into it. The main DGX station, the bigger one, uses that GB300 Ultra chip. Picture this. It's a 72-core Grace CPU based on ARM's architecture, which is interesting in itself. Paired directly, and I mean directly, with their new Blackwell Ultra GPU. It's all tightly integrated.
72 CPU cores. Okay, that's a hefty number, even for workstations. But we see high core counts sometimes. What makes this specific pairing so special? What's the Ultra part?
It's less about just the core count and more about how everything interacts, especially the memory. This is the part that makes you pause. The new DGX station supports up to 784 gigabytes of unified memory. That is a vast amount.
Whoa, okay. 784 gigabytes? Of DRAM? On a desktop system? My fairly decent laptop has 16 gigabytes. What does anyone do with nearly a terabyte of memory locally?
Chuckles. It sounds almost fantastical, right? But this isn't for checking email or writing reports. This is laser-focused on AI developers, data scientists, researchers. Folks training large language models, complex physics simulations, drug discovery models. Those workloads are incredibly memory hungry.
Okay, so huge datasets, complex models that need tons of parameters loaded up. That makes sense. You mentioned unified memory. Does that work like integrated graphics on a laptop, where the CPU and GPU share the same pool, just way bigger?
Conceptually similar, yes, but executed on a completely different performance level. It combines 288 gigabytes of extremely fast HBM3E memory. That's high bandwidth memory sitting very close to the GPU, with 496 gigabytes of slightly less rapid but still quick LPDDR5X system RAM. The unified aspect means both the Grace CPU and the Blackwell GPU can access this entire 784 gigabytes pool without constantly copying massive datasets back and forth across a slower bus like PCIe. It's about reducing those data transfer bottlenecks that can stall AI training.
Ah, I see. So, less waiting around. Instead of the GPU asking the CPU for data via PCIe and waiting, or vice versa, they can both access the relevant parts of this huge shared pool much more directly. That definitely seems advantageous for AI.
Precisely. And that direct connection is facilitated by NVLink. Specifically, their 5th-generation NVLink using a chip-to-chip, or C2Cs, interconnect. This is the high-speed fabric binding the Grace CPU and Blackwell GPU components together within that GB300 Ultra chip.
NVLink. I know that's Nvidia's special sauce for linking multiple GPUs in big servers. How fast are we talking for this chip-to-chip version inside the station?
Get this. 900 gigabytes per second of bidirectional bandwidth between the CPU and GPU complex. Just for context, The latest PCIe Gen 5 standard, in a full X16 slot configuration, offers around 128 GB per second. So, NVLink-C2C is operating in a totally different performance bracket. It's about minimizing latency and maximizing throughput, right where the computation happens.
Okay, 900 gigabytes per second. That's like having a dedicated, multi-lane private highway directly connecting the CPU and GPU, while PCIe is more like a busy public road. Data just moves instantly where it needs to.
That's a perfect analogy. And it's critical when you're dealing with AI models that might have trillions of parameters. Moving the model weights, the training data, the intermediate calculations. Doing that quickly is paramount.
So we've got the potent chip combo, the enormous unified memory pool, the super fast internal connection. What about connecting to the outside world, or linking multiple machines? Is this purely a solo powerhouse?
Well, a single DGX station is indeed a powerhouse, but they've definitely considered scaling. It incorporates the new CONNECTX8 Super NIC, and Super NIC isn't just marketing fluff. This isn't your standard office Ethernet port.
Super NIC. I'm intrigued. What makes it super?
It's an ultra-fast network interface card capable of up to 800 gigabits per second. This is designed for high-speed clustering, linking multiple DGX stations together, or connecting them to high-performance storage networks or larger DGX clusters. It uses technologies like RDMA over Converged Ethernet, or RoCE, which allows one computer to access memory on another computer directly over the network with very low latency.
800 gigabits per second. Wow. So, if one station isn't quite enough for your giant model, you can potentially link several, and they can communicate almost as if they were one system? Essential for distributed training, I imagine.
Exactly right. Minimizing that network latency is crucial when you're trying to synchronize calculations and updates across potentially hundreds or thousands of GPU cores working in parallel on the same problem. It helps a cluster of machines behave more like a single, cohesive computational unit.
Okay, the DGX Station sounds like an absolute monster, aimed at serious AI research and development. But you mentioned a second one, the DGX Spark? What's the story there?
Right, the Spark. Think of it as the station's much smaller sibling. Nvidia actually called it a mini PC, which feels a bit understated given its potential, but gives you an idea of the form factor. It's expected to use a scaled-down version of the Grace Blackwell architecture, likely a GB100 superchip variant, still heavily optimized for AI tasks, but in a more compact package.
And crucially, the price point? Because those previous DGX stations cost, well, let's just say you needed a serious budget. Is the Spark more approachable?
That's perhaps the most interesting part. Nvidia announced the Spark time starts at $2,999. Now compare that to the full DGX station. Official pricing isn't out, but based on history and the components, estimates are easily in the high tens of thousands, maybe even north of $50,000. Or $100,000 depending on configuration. But $3,000 for the Spark? That puts it in a completely different ballpark.
Okay, $3,000 is still a premium price tag for a desktop, no question, but it's worlds away from $50,000 plus. It suddenly makes it comparable to high-end professional workstations, maybe even Apple's Mac Studio range?
That comparison is definitely being made. A well-spec'd Mac Studio with an M-series Ultra chip can easily run you $6,000 or more. Both are powerful desktop systems using that integrated CPU/GPU approach with unified memory, targeting professionals. But their focus differs.
Right. I always associate Mac Studios with creative work, video editing, 3D rendering, music production. That seems to be their stronghold.
Correct. And while a Mac Studio can certainly run AI models, especially using Apple's own frameworks and neural engine, the DGX Spark, even at its entry point, is purpose-built for AI development and inference. It's designed to leverage Nvidia's entire CUDA software ecosystem, its dedicated tensor cores, for accelerating specific AI math operations. It's optimized for that particular type of workload in a way the Mac Studio isn't. The research suggests the Spark delivers around 1 petaflop of AI performance.
1 petaflop. Remind me what a flop is again, in simple terms?
Sure. It stands for floating point operations per second. It's a standard measure of computing power. A petaflop is 1,000 trillion, or 10 to the power of 15, of those operations per second. Now that number is often quoted using lower precision math formats commonly used in AI inference tasks, like FP8 or FP4, so it's a benchmark figure, but it gives you a sense of the raw computational throughput.
1,000 trillion operations a second on a $3,000 mini PCs. Okay, so Mac Studio leans creative, DGX Spark leans AI developer. Even if their price points might overlap a bit depending on configuration?
That seems to be the strategic positioning, yes. Nvidia is clearly aiming at individual developers, smaller research teams, AI startups, maybe university labs that need substantial local AI compute power but can't justify the expense or infrastructure for a full DGX station or continuous heavy cloud usage.
It feels like a significant move, bringing this level of specialized compute out of the data center shadows and onto the desktop. I think I saw a quote from Jensen Huang, Nvidia's CEO, saying something like, "This is what a PC should look like?"
He did say something to that effect during the GTC keynote, yes, and it points towards their vision. Future personal computers won't just run *AI software. They'll be fundamentally architected for *AI development and deployment. It's about designing the hardware from the silicon up, with AI as a primary, not secondary, workload.
Which makes sense, given how AI is integrating into almost everything. But, Mark, it also raises some important questions, doesn't it? You mentioned the counterarguments section in our research notes. Even the Spark at $3,000, while cheaper than its big sibling, isn't exactly pocket change. Does this risk widening the gap between those who can afford these powerful tools and those who can't?
That's a very valid point, Jenny, and it's a concern echoed in the research. While it's more times accessible than, say, a $100,000 machine, $3,000 is still a substantial investment, especially for students, independent researchers, or startups in less well-funded regions. It does democratize access to a certain times level of AI compute, potentially shifting some power away from being purely cloud-dependent. But it doesn't instantly make top-tier AI development affordable for everyone. It's a step towards democratization, but the broader accessibility challenge certainly remains.
And there's the ecosystem aspect too, right? The research mentioned dependency. These machines are built around Nvidia's CUDA platform. Does that mean users get locked into Nvidia's way of doing things?
That's the trade-off, often. Nvidia's ecosystem, CUDNN, TensorRT, all their libraries, is incredibly mature and well-supported for AI. That's a major advantage. However, at times largely proprietary. If you develop primarily on these systems, your code and workflows are deeply tied to NVIDIA hardware. Moving to a different architecture, say from AMD or Intel, or a specialized AI chip startup, might require significant effort. So yes, there's a potential for vendor lock-in, which can limit flexibility down the road.
So convenience and performance now versus potential lack of flexibility later. And what about the environment? Hacking so much power into these boxes. Do we know anything about their energy consumption? AI training is notoriously power-hungry.
That's another critical point raised in the research, and NVIDIA hasn't released detailed power consumption figures for these specific desktop models yet, especially under full load. However, generally speaking, high-performance computing consumes significant energy, while the Grace CPU, being ARM-based, might be more power-efficient per core than traditional x86 CPUs. The sheer density of compute means these machines will draw substantial power. Data center efficiency is a huge focus, but bringing that power to the desktop level does raise questions about the aggregate energy footprint if these become widespread. It's something the industry needs to keep addressing. Performance per watt is a key metric.
Okay, so cost, potential ecosystem lock-in, and environmental impact are definitely things to watch. One more angle from the research. Are these machines only times good for AI? Could you use a DGX Spark for, say, high-end video editing or other demanding tasks? Or is it too specialized?
That's a good question. While the architecture is heavily optimized for AI's parallel processing and matrix math, the Grace CPU component is still a capable ARM processor. You likely could run other software on it, possibly even general productivity tasks if needed. However, It's unlikely to be the most cost-effective or performant solution for tasks like video editing compared to a system specifically designed for that, like the Mac Studio, or a high-end PC workstation with a consumer GPU. The value proposition of the DGX Spark is squarely aimed at its AI capabilities. Using it primarily for other things might be like using a Formula One car for grocery shopping. Possible, but not really the intended or most efficient use.
Got it. Right tool for the job. So, considering all this, who do you see being the early adopters for the Spark besides the obvious Nvidia partners?
I'd expect university research labs focusing on AI, smaller AI-focused startups, perhaps specialized data science teams within larger corporations who need dedicated hardware for prototyping or exploring models without incurring huge cloud bills or waiting for shared cluster resources. And Nvidia mentioned partners like Dell, HIP, and others will be offering systems based on this later in the year, so we might see different configurations and maybe slightly different price points emerging too.
It really feels like the landscape is shifting. This idea of desktop supercomputing for AI becoming more attainable. The research suggested a fair number of companies might deploy systems like these locally in the near future.
Yeah, projections do point towards more on-premise or localized AI compute. There are several drivers: trying to manage unpredictable cloud spending, concerns about data privacy and security for sensitive datasets, and the need for lower latency for certain real-time inference tasks. Having that power right there can significantly speed up iteration and development cycles.
So maybe the future isn't strictly cloud or times local, but a hybrid approach. You use powerful desktops like the Spark or Station for development, experimentation, maybe smaller model training, and then scale up to larger cloud instances or dedicated clusters for the really massive final training runs?
I think that's a very likely scenario. These desktop systems fill a crucial niche between consumer-level hardware and massive data center infrastructure. They provide a dedicated, high-performance sandbox.
It's fascinating stuff. It really does feel like the definition of a personal computer, or at least a professional computer, is evolving right in front of us.
It truly is. We're moving from general-purpose machines that times run AI to specialized machines times designed time for AI, and they're starting to become more accessible. It's an exciting, and maybe slightly intimidating, time in tech.
Well, thanks for navigating us through the DGX Station and Spark announcements, Mark. My brain feels less fuzzy and more, loaded with information. Still wrapping my head around 784 gigs of RAM, though.
Laughs times you and me both, Jenny. It's a number that definitely makes an impression.
All right, that's all the time we have for today on Tech Forward. We covered a lot, from silicon specs to accessibility and environmental questions. What do you think about these new AMI desktops? Do you see them changing how AMI development happens? Or are the costs and potential lock-in bigger concerns?
Yeah, we'd love to hear your thoughts. Find us on social media, just search for Tech Forward Podcast, and let us know. We might even feature some listener comments in a future episode. Maybe we'll run a poll on whether these systems democratize AI or concentrate power.
Great idea. Look for that poll. Until next time.
Keep exploring.